Today, we'll be looking at how new liquid AI learns continuously from its experience of the world. If you're new to this channel, welcome. This is Mr. Singularity, where we explore the scientific and technological breakthroughs shaping the future as we know it. AI is still not anything like humans, with all the similarities to the human brain. Maybe that's all right. The brains of the animal kingdom come in all shapes and sizes. So in a modern machine learning approach, researchers have gone away from the human brain and all of its beautiful complexity, turning now to the brain of a lowly worm for guidance. Turns out, convenience has its advantages. The resulting neural network is efficient, transparent, and here's a kicker, a lifelong learner. Whereas most machine learning algorithms can't develop the capabilities past the initial training cycle, researchers say the latest technique, called a liquid neural network, has a kind of built-in neuroplasticity. That's how it works, say, in the future. Maybe driving a vehicle or steering a robot. It can learn from experience and change its connections on the fly. Such adaptability is important in an environment that is noisy and unpredictable. The architecture of the algorithm was inspired by the mere 302 neurons that make up the C nervous system. Elegans, a small nematode, or worm. The work published last year, which includes MIT researchers and the Austrian Institute of Science and Technology, say that despite its simplicity, C. elegans are capable of unexpectedly fascinating and diverse actions. So they created equations to mathematically model the neurons of the worm and then design them into a neural network. The worm brain algorithm was much simpler than other cutting-edge machine learning algorithms, but it was nevertheless capable of performing comparable tasks, such as holding a car in its path. Today, deep learning models with millions of parameters are often used for complex learning tasks such as self-driving. However, our current strategy helps us to reduce the scale of the networks by 2 orders of magnitude. Our programs only use 75,000 training parameters. Today, in a new article, the group is continuing its worm-inspired framework by introducing a whole new capability. Fresh tricks, old worm. The performance of the neural network, turning the steering wheel to the right, for example, depends on the collection of weighted relations between the neurons of the network. It's the same thing in our minds. Each brain cell is linked to a variety of other cells. Whether or not a given cell fires depends on the number of signals it receives. Beyond any threshold or weight, the cell sends a signal to its own network of downstream connections. These weights are considered parameters in a natural network. When the device feeds data across the network, its parameters agree on the configuration that produces the best performance. Typically, the parameters of the neural network are fixed into place during preparation and the algorithm is put to work. But in the real world, this can mean it's a little brittle, showing an algorithm that deviates so much from its preparation and it's going to crack. Not the desired outcome. On the other hand, in a liquid neural network, parameters will begin to evolve with time and with practice. The AI knows about the work. This adaptability means that the algorithm is less likely to fail when the planet launches fresh or noisy information, like for example when rain obscures the camera of an autonomous vehicle. In comparison, unlike broader algorithms, the inner workings of which are largely inscrutable, the basic design of the algorithm helps researchers to peek in and inspect their decision-making. Neither his new ability nor his still diminutive size appeared to hold the AI back. The algorithm worked as well or better than other state-of-the-art time sequence algorithms to predict the next steps in a series of events. Everyone is talking about scaling up their network. We're trying to scale down to have fewer but richer nodes. An adaptable algorithm that requires very little computational resources will make a perfect brain robot. Hasani claims that this methodology could be useful in other applications requiring real-time analysis of new data, such as video processing or financial analysis. We have a more expressive neural network that is influenced by evolution, but this is only the beginning of the process. The obvious question is, how are you going to expand this? We assume that this kind of network may be a core element of future intelligence networks. Is bigger better? At a time when major players like OpenAI and Google are constantly making headlines with gargantuan machine learning algorithms, this is an interesting example of an alternative strategy in the opposite direction. OpenAI's GPT-3 algorithm jointly fell jaws last year, both in terms of size, at the moment a record-breaking 175 billion parameters, and its capabilities. A new Google algorithm led the charts with more than 1 trillion parameters. Yet critics complain that the move to even greater AI is inefficient, costly, and consolidates science into the hands of a few cash-based firms to finance large-scale models. Furthermore, these big models are black boxes. Their acts are largely impenetrable. This can be highly troublesome when unsupervised models are educated on the unfiltered internet. There's no knowing, or maybe controlling, what bad habits they're going to pick up. Academic scholars are gradually working to resolve some of these problems. As businesses like OpenAI, Google, and Microsoft push to confirm the larger-than-better theory, serious AI advances in productivity are expected to appear elsewhere. Not in lieu of lack of capital, but because of that. Necessity, as they claim, is the mother of creativity. What's your take on this? Let me know down in the comments below and check out one of these other videos. This has been Mr. Singularity, and I'll see you on the next one.